Introduction. Welcome, curious minds, to an electrifying journey into the world of ionic bonds. Brace yourselves as we explore the mesmerizing dance of oppositely charged ions, from the intricate lattice structures they form to the real-world applications that harness their incredible power. Ionic bond basics. Picture ions as atoms that have embraced the art of giving and taking electrons. When a giver atom loses electrons and becomes positively charged, and a taker atom gains those electrons, they're irresistibly drawn together by an ionic bond. Imagine it like a cosmic dance of attraction. Lattice energy and size effects. Think of ions like puzzle pieces fitting together. The stronger the attraction, the tighter the fit. Lattice energy, the energy released when ions come together, is like the applause when the puzzle's complete. Bigger ions may struggle to fit perfectly, but small ions join like a snuggly puzzle. Covalent character in ionic bonds. Here's the twist. Sometimes, ionic bonds decide to get cozy with a touch of covalent character. Imagine them holding hands in a dance, sharing electrons to some extent. This blending is like a duo that dances seamlessly yet maintains their individuality. Conductivity in ionic solids. Hold on to your seats for this mind-blowing fact. Ionic solids, like table salt, can conduct electricity when molten or dissolved. The ions free up to move around, carrying charges with them. It's like ions breaking free from a dance formation to start a lively parade. Crystal structures and imperfections. Close your eyes and envision a crystal structure, a symmetrical arrangement of ions. But wait, perfection is overrated. Imperfections, like missing ions or extra ones, add uniqueness. It's like a dance troupe with a mix of dancers, creating a mesmerizing performance. 1. Stoichiometric defect. In this kind of point defect, the ratio of positive and negative ions, stoichiometric, and electrical neutrality of a solid is not disturbed. Sometimes it is also known as intrinsic or thermodynamic defects. Fundamentally, they are of two types. Vacancy defect. When an atom is not present at their lattice sites, then that lattice site is vacant and it creates a vacancy defect. Due to this, the density of a substance decreases. Interstitial defect. It is a defect in which an atom or molecule occupies the intermolecular spaces in crystals. In this defect, the density of the substance increases. A non-ionic compound mainly shows vacancy and interstitial defects. An ionic compound shows the same in Frenkel and Schottky defect. 2. Frenkel defect. In ionic solids generally, the smaller ion, cation, moves out of its place and occupies an intermolecular space. In this case, a vacancy defect is created on its original position and the interstitial defect is experienced at its new position. It is also known as dislocation defect. The density of a substance remains unchanged. It happens when there is a huge difference in the size of anions and cations. Example, ZNS and silver 1 chloride. 3. Schottky defect. This kind of vacancy defects is found in ionic solids. But in ionic compounds, we need to balance the electrical neutrality of the compound so an equal number of anions and cations will be missing from the compound. It reduces the density of the substance. In this, the size of cations and anions are of almost the same. Impurity defect. Let's understand the impurity defect by an example. If molten sodium chloride is crystallized with SrCl2 compound, then the senior 2 plus ions replace 2 Na plus ions and occupy the place of 1 Na plus. In this way the lattice site of 1 Na plus is vacant and it creates an impurity defect. Non-stoichiometric defect. In this defect, the cations and anions ratio is disturbed either because of adding or removing of ions. Types of non-stoichiometric defect. Metal deficiency defect. In this, the solids have less number of metals relative to the described stoichiometric proportion. Metal excess defect. There are two types of metal excess defect. Metal excess defect due to anionic vacancies. This occurs due to the absence of anions from its original lattice site in crystals. Therefore, instead of anions, electrons occupy their position. Metal excess defect due to the presence of extra cations at interstitial sites. Here, on heating the compound, it releases extra cations. These cations occupy the interstitial sites in crystals and the same number of electrons goes to neighboring interstitial sites. There is so much to learn about the crystalline solids, its structure and its defects. This is just the overview of point defects in solids. Applications of ionic bonds. Hold your breath for the finale, real-world magic fueled by ionic bonds. Batteries, powered by ions shuttling back and forth, keep our devices alive. Ever heard of ceramics? The strength of pottery and tiles comes from ionic bonds holding them together. Conclusion. As our electrifying journey comes to an end, remember, ionic bonds are more than just a scientific concept. They're the architects of the structures we use and the power we harness. From the crystal lattice formations to the heartbeat of technology, ionic bonds continue to amaze us. So, keep your eyes open, the dance of charges is happening all around us.